get to the mean and expected value. What were the three things we learnt yesterday? Name me one thing. What did we learn yesterday? Let's go with Richie. What did we learn yesterday? Yeah, yesterday. 13C. What were we dealing with? No clue. Let's go with, yes, Anna. Discrete. Yes, very good. We had discrete versus what, Richie? Continuous. Continuous. We had two types of data. Yeah, two types of data. You had either discrete or you had continuous. What was the definition? Martin, there's plenty of chairs here. What was the definition of a discrete data? Yes, Aaron. Very good. Heads and tails is an example where there's no in-between, and what we're trying to say, which is what Sian said, it's countable. Okay, so we had heads and tails, you can count that. We had males in our classroom, that's countable. You can count the number of males in here. What else can you count? Give me an example, Ben. Females. Number of females in this classroom. Something a bit more, something a bit different. Something a bit different. Give me another one. Let's go, Sian. Give me. Am I wrong? No, you're not wrong. Give me another example, Sian, of a discrete data.
Number of hairs. Number of hairs.
Yeah, number of hairs. You can count that. What else can you have? Instead of numbers of, what else can I have? Let's go, Steph. Give me another example.
Chairs.
Number of chairs, number of tables, number of cars. I want something different here. Sizes of what?
Shirts.
Shirt sizes. Small, medium, large. That was different. Okay. What else? What else can you have? Yes.
House numbers.
House numbers. It's 1, 2, 3, 4, 5. It's countable, right? You can have shoe sizes. You got your 10, 10 and a half. You got your 12, 12 and a half. It's all countable. Okay? Yes. Now, if that's discrete, if you had time, yes. Now, if that was discrete data, then what is continuous? Give me an example of a continuous data. Let's go with Alessia. Hair color. Hair color, you can still, technically you can count it. You can describe it. So you can say black, white. You can count the number of blacks, you can count the number of whites, you can count the color. Okay? But I'm looking for something that you, unless you're talking about a spectrum. If you're talking about a color spectrum, then in your color spectrum there's
always shift.
Yeah, there's always slightly in between, and that's hard to count in total, right? Then that's a fair call. Then color, yes, color scheme. What else is continuous? Give me another one.
Number of decimals of pi. Number of decimals of pi. Number of decimals of pi.
Number of decimals of pi. I think you can count that, but because it's continuous, it goes on. You can't count. But it's not a data though. It's not. I'm looking for a measurement. A data. Data is something that you can collect and analyze. But I guess you can analyze and collect number of data or number of decimals of pi. It feels very limited, but I guess you could. Give me something else that you actually would encounter in a maths problem. Not a decimals of pi. Give me something else. Yes, Aaron.
Wow.
Time. Give me another one, Trent.
Like growth over time. Like, because like your height, yeah, like your height. Let's say I'm growing 5 centimeters a year, so like you could continuously grab that. You could.
Yeah, but I feel like you're measuring two things right there, because when we're talking about data, we have a measurement of a particular variable. In your case, I think you're talking about a rate. Is that what you're talking about? So it's height by time, so it's a rate. So your rate is by time. But that's the thing, your rate is measured by two variables. It's height and time. And that's what I'm saying. So height and time, because what if you were measuring a rate where one is a discrete and then the other one is a continuous? Then what do you call that? Is it continuous data or is it considered discrete data? So I think taking it apart, the rate is broken up into two parts. Height is continuous, time is continuous. So that was the first thing we learnt from yesterday's lesson. I talked about the difference between discrete and continuous. Why did you need to know that? Because it separates how you would calculate it. If you can count the number of the data, then that means you can find the probability because you know the total. If you know the total, you can find the probability, like rolling a dice. total number of options, you've got 6 options. That's why you know the chance of getting a 1 or a 2 or a 3 is 1 out of 6. But for continuous, you can't. That's why when you get to chapter 16 onwards, you're going to have to use a different technique to find the probability, okay? So that's why, first part, to know the difference between the two, that was number 1. What was number 2? There were 3 things you were meant to take out yesterday's lesson. What was it again? Will? Oh, you weren't there, sorry. Athena? There are 3 things that I wanted you to take out of yesterday's lesson. Probability distribution table. Probability distribution. What is that? Someone describe to me. What is probability distribution table? Can I please? Let's go, Michael. Perfect. Excellent. Outcome, which is your X. So if you remember from last session, X is your data. We already said that we now know that discrete is the type of data we have. X represents what we're doing with that data. So in that case, are we counting the data? So in this case here, it's counting the number of chalk chips. So chalk chips becomes the X variable, and that variable is a type of data, and that's a discrete data. Putting it into a table like we have now is called a probability distribution. Why? Because that means when you sketch this graph and you distribute it, it is now x-axis by not the y-axis, but it is the probability axis. So the y-axis is your probabilities now. Okay? So that was one to understand the table. So you had probability distribution, and then I said that the other thing I wanted you to take out of that lesson was what? So you had probability distribution, you had discrete, you understood what discrete was. Chapter 13, this is the first time we've introduced it. What else do I also introduce as a new thing? No, that's today's lesson, which I haven't described. What else? It's on this page. The given is from conditional probabilities, 13B. What's here that I talked about yesterday? Say it again. No, that goes with probability distribution. So that's point number 2. Right in front of you. Well, I guess, yeah. What would you say? Given, intersection, but really I was talking about reading the language, set notation. Yeah. Yeah. Now I know it sounds pedantic, but that's where I said the key part. I said the hardest part of yesterday wasn't about doing this. It wasn't about knowing your probability distribution. My point yesterday that I said was the hardest was knowing how to represent X, how to model X. Because modeling X will determine how you're going to solve everything else. If you figure out what your goal is and what X represents, you get that right, the rest is easy. Because the rest, like, you guys knew how to answer this straight off the bat when we were doing yesterday. But the hardest part was understanding what X is. And what we spent a lot of time yesterday was this. This is what we were doing yesterday. Do you remember when I showed you PR of capital X equals little x, and we had a lot of confused faces, right? And I said the hardest part was understanding notation. So now, breaking it apart again, notation, set notation. This just means PR represents probability. So it means chances of X equals to little x. The capital X is what you're representing. It's the data. What is it representing? In our case, chances of X here represents number of chalk chips. So if I were to read this, this means what are the chances of having the number of chalk chips equal to whatever it is I'm looking for. So the number of chalk chips could either be 2, 3, 4, 5, 6, or 7. I don't know which one I'm talking about. So if I wanted to know what's the chance of getting 2 chalk chips in this brand, then I would write PR of capital X equals to 2. Now I'm saying that the data is equivalent to 2. And what's the data representing? It is the number of chalk chips. So therefore, writing this represents a sentence where you're saying the chances of, getting 2 chalk chips, or the chance of getting 2 chalk chips is, and therefore, okay? And the reason why I'm emphasizing that, because when they write you the question in itself, you have to rewrite that as a set notation to know what you're doing. Because if you figure out what the goal is, and you know what they're trying to ask you to do, it's easy to do. Because right now you're answering the question, they gave you the notation, they tell you x greater than equal to 4. X greater than equal to 4 given that x greater than 2. But when you actually do the questions in the exams, they don't have it like this. How they have it is a worded problem. So they'll say things like, you know, I want you to find the chances of, you know, 2 of the same thing occurring. Then you have to know that this means 2 or more. Okay, 2 or more. So you have to do x greater than or equal to 2. But that's on you to figure that out. And that's why I'm saying these are easy, because they tell you what to do and they gave you a distribution and you know what x represents. That's why it's easy. The hardest step is for you to figure out what x represents and how that plays out, how you're going to solve it. Okay, and that's the difference between choosing either you're going to use chapter 14 for binomial, or whether you're going to do normal distribution or you're going to do sampling. The only way for you to know is reading that question and what x represents. Okay? As a language, yeah. Yes. All right, so now, today's lesson. So I just recapped what we did yesterday's lesson. We had 3 things. We wanted to know what discrete was. We wanted to know what probability distribution was. And I mentioned about how to read the set notations being very important. Being able to describe what x represents. Now today's lesson, expected value. On the side, I wrote mean, because the expected value is the mean, and the mean back in year 7, how do you calculate the mean again? What do?
You count and you count them together and you divide by the number.
Good. You count number of numbers, you add them all together and divide by number of numbers, right? Another word for that was, starting with A?
Average.
The average. Okay, we're not doing anything different. I'm going to show you something here, what we're doing today. There's another 3 things I wanted to learn in today's lesson. One's called the expected value, the other one's called variance, the last one's called standard deviation. And my aim is to put them all into a picture so that you understand what they mean. Because if you get the theory, it applies to all of the chapters. So the hardest part is getting chapter 13 first. Okay? So here we go. Expected value, which is the average. And the average just means, or the expected value means in the long term, on average, what is the outcome? What do you expect? Okay? Now the example I gave you is here. This example here, when I ask you, if you flip a coin and I say, what's the chance of getting tails? What would you tell me? 50%, right? 50% chance of getting tails or 50% chance of getting heads, right? And if I told you that I flipped the coin 1,000 times, how many of those 1,000 times do you expect to have tails and H's? 500 each. Now, how did you get to 500? What'd you do? No, right now, why was it 500, 500? What did you do in your head just now to get 500, 500? Let's hear. And that's key. What we just said just now, you just said the expected value, what you expected was 50% of the number of trials I did. So in this case here, it's 0.5 times x in terms of what the data is, number of times I did, right? Okay, now, I want to get you to think about this problem and just keep that in mind, yeah? 50% of x, 50% of that gave you the expected value, okay? Now, let's look at this problem. We're going to use a distribution table. But first, remember what was the hardest part of probability is to make a distribution table is what you're defining. Okay, what is x representing? So let's look at this problem here. Person may buy a lucky ticket for $1. So I go out, I buy a ticket for $1, so I spent $1. And then they have a 20% chance of winning $2. A 5% chance of winning $11. And otherwise they lose. Now, before you answer the question, is this a good game to play or not? Yes. Okay, yes or no, but then the question is, by how much are you winning or are you losing, and how do you know? Because, okay, now your goal is to find out in the long term, am I gaining or am I losing? True? Okay, because the only way to know if this is a good game is if you're gaining. Yeah? If you're gaining, that means you're profiting. If you're losing, it means you're losing money, right? So, your goal now, when you're modeling this question and what x represents, what we just did was we just said, are you gaining or losing? Now let's say if I won $2, but I bought a ticket for $1, how much am I really gaining? $1. So now I've got $1 for what I'm gaining. And then what if I bought $1, but then I won $11? How much am I really winning? $11. But then if I bought a ticket for $1 and I didn't win, okay? If I didn't win, then how much am I really gaining right now? -1. So it was -$1 or -$1, and then the other one was I gained $1, or the other one I gained $10. True? So I had -1, 1, and 10. Now what is that representing again? How much? How much I'm winning or losing. It's profiting, right? So X now, in terms of my distribution, I've got an idea. I've got an idea because the chances was 20% chance of gaining $1, 5% chance of gaining $10, and otherwise I'd be losing $1, right? So let's write this out. If X represents profit, then the possibilities that I could have was either lose $1, gain $1, or gain $10. He told me that this was 20% chance, actually no, 20% chance and 5% chance of gaining $10. Then what's the chances of me losing $1? 75% logically, right? So logically, they all have to add up to 1, 75% chance. Now that's my distribution table. In order to get here, you have to question, what does it mean by, is it a good game? And from the good game, you can only tell if you're gaining or losing. That's how you know if it's a good game or not. By how much? This is how I've got my distribution table, right? Now.
He's
not wrong.
Oh, sorry. Okay, now we're just... All right, we're not in a philosophy class right now. We're just going to go with mathematics logically.
Written like that in your exam. Is it a good game to play?
Oh, they wouldn't write like that. No. They wouldn't write that. They wouldn't write that, Mazen. If you got that, you have every right to complain the way you are right now, but you know that's not the case. It's not going to be like that in the exam, okay? So, here we go. We've got a distribution table. Now, we just said again, to find the expected value, because in the long run, I want to know, am I gaining or am I losing, right? So, my goal is to find the average. Now, how do you find the average again? You guys told me it was? Add all the numbers together. So, I need to add all my profits together, and then divide it by the number of profits or the number of numbers that I had. Now, in this case here, I don't know how many tickets I'm buying. It can't just be one. I don't know what the chances are there. So let's say I'm going to put a hypothetical here now. Let's say I bought 1,000 tickets. I played this game 1,000 times, hypothetically, okay? And I want to ask you later, does it matter if I play 1,000 times or 1,000,000 times or 10 times or once? What changes, okay? But right now I'm going to go with 1,000 because I think it's a bit more than 100 and it's less than 1,000,000 or less than 10,000, right? Let's say I play 1,000. So out of those 1,000, how many games am I expected, which is what we did before, am I expected to gain $10? How do you figure it out? It should be 50. How'd you get 50? How'd you get 50? What'd you do, Trent?
I know when it's 100, it'll be 5. If you add 0, add 0 to 5.
Because what you're actually doing is, I said there's a 5% chance of you getting 10. So what you expect is 5% of 1,000, which is 50. Just like what you did before, you did 50% of 1,000 to say 500 for heads for 500 for tails. I'm doing the same thing now, that you got 5% of 1,000, which is 50 games. Okay, 50 games when you earned $10. What about the number of games that you would gain $1? How many games would that have to be out of 1,000? 200, okay? So we've got 200 games. How'd you get 200? Same thing again. We're doing 20% of 1,000, which gives you 200. And then finally, if it's 75% of 1,000, how much would that be? Okay, so I've got 50 games that I'm losing $1. I've got 200 games that I'm gaining $1. And I've got 50 games I'm gaining $10. Now, we said before, to find the average, you have to add all of the profit and then divide that by the number of numbers or number of games that I've got. Now, number of games I've got is 1,000. So, if I were to find the average, this is what you would have said. To find the average, it's out of 1,000, and I've got -1 plus -1 plus -1, and I've got 750 of them. So let's simplify that. If we got 750 of these -1s, in total I have -750, because you did, this is what you did here. You said there's 750 of these expected. You're expecting 750 groups of these negative ones, okay? Plus, next group, I've got 200 of these $1. Plus, I've got 50 of these $10. True? We follow that and we get our answer. Whatever that answer is, that is my expected, right? Now here's my question. Well, not my question, but I want you to see something here. Let's take a step back from this line here. This is how you find the average. Okay, we haven't done anything different. We just did add. But I've simplified the, instead of adding -1 750 times, instead of adding 1 200 times, instead of adding 10 50 times, I've simplified it, right? This is the average. Now from the average, I want you to see this. How'd you get 750 again? What'd you do? You did 75% of 1,000. I'm going to write all this in so you can see 750 was actually the result of doing 0.75 times 1,000, 1,000 times the -1 there, right? The 200 came from doing 0.2 times 1,000 times the 1, and then the 50 came from 0.05 times 1,000 times 10. Okay? So we're saying 750, where'd you get that from? It was 75%, 0.75 times 1,000. So that's what I'm writing. 0.75 times 1,000, 750, times that by -1. And the nice thing here is because I'm timesing 1,000 for this term, and I'm timesing this term by 1,000, I'm also timesing this term by 1,000, but I'm also dividing them all by 1,000. Ooh.
No way.
Uh-huh.
No way.
So, if this all cancels out, I end up with 0.75 times -1 plus 0.2 times 1 plus 0.05 times 10, which essentially is what, when you're finding the average, you're just multiplying these. You can see what we're doing there? So now going back to my question before, I said, does it matter if I chose 1,000 games or 1,000,000 games or 10 games? No, the answer is no. Okay. Now, if you did this on your calculator, if you actually calculated this, you end up with -0.05. But what does that mean? See, I'm all about interpretation here. It's not about the answer. What's -0.05 represent when I do that bet? Very good. For every game that you buy, so every ticket that you buy, for every game you invest in, you're losing expected. So that doesn't mean that you will. It's an expectation that you're losing 5 cents. But you can only see that in the long term, because what we calculated just now is an average. It's an average for long term. Does that make sense what average means now? It's not for one instance, because if we all now flip the coin, it doesn't actually show us that 50% chance you're going to get heads or tails. But in the long run, it's likely we're all going to get about 50%. That's what it means by average. Yeah. So now that we know average, and this, what I just showed you just now, why I didn't give you the formula for the expected, because I wanted you to see what it meant by expected, because expected is actually just the average. So right here, this is what your session's about. I'm just going to delete everything. If you actually look at it, this is what your textbook will tell you. Right there is your formula. And you didn't need to know that formula, because like, logically, that's where it was coming from. That you can just take the sum of all your data times the chances of that data occurring, which is what we were doing before. Data times the chances, add them together, gave you the average. It's not a random formula, it just came from the fact that when you're finding percentages, it doesn't matter how many games you play, that's how you find the long-term average. Cool? So this is nothing scary, it's just what we just did. Sum of all numbers divided by number of numbers. How do we feel about that? Does that make sense? Yeah? All right, excellent. Now, that's one down. I've got 2 more points to do it. Yeah? So we got expected value. Now, just a few more things about the expected value before we go to variance and standard deviation. The one thing I want you to realize is when you write E, that means find the average, find the mean. Of X, X is the data. Data is depending on what data you're dealing with. It could be discrete, it could be continuous, it could be whatever it is, it could be a function. In our case here, whatever X represented, it was X times the chances of that occurring. Same thing here, if you say E of G of X, then you're saying now it's a function. Okay, so sometimes the probability might not just be the data itself, it could be a pattern. The data might be going in a pattern, such that if you chose 3 chocolate chips, there was a pattern to get to the next one was 3 chocolate chips times 2 plus 1 gives you the actual data. Then maybe there's a pattern to it. Maybe there's a linear pattern to the data. Maybe there was a quadratic pattern to the data. So we say the data is in terms of a function g of x, right? So that means when you're finding the expected value, it's the same deal. Instead of x times the chances of it occurring, it is now the function of x times the probability. And this is really key when you get to chapter 16, 17, 18, when we do continuous data, it will be a function. And because it's a function, the theory still goes the same. So that's what I'm saying. Chapter 13 is all about theory. Get the theory down, every other chapter makes sense. And this is where it's all coming from. So it doesn't matter what this is. And this is why I'm saying, because when I teach it every year, students will get confused between this. E of x, no one has any issues with that. Everyone's like, yeah, it's sum of x times p of x. But as soon as I do this, e of x squared, and I ask, what does that mean? And students will be like, I have no idea what he just said. What does it mean if I said e of x was x, the data x, times the probability, and sum them each one, sum them all up? What does it mean if I said e of x squared? What does that mean? Yeah. So if you were to do this, this literally just means sum all the x squares and then times by the chance. So if I were to go back to our table just now, if this was my x, and I want to find the expected value of x squared, then it's just -1 squared, so -1 squared times 0.75, plus 1 squared times 0.2, plus 10 squared times 0.05. There's no trick to it. It's just whatever you're doing the expected value of, you're just replacing that data. Okay, I'm going to be asking that all the way through until we finish up to chapter 18. I'm going to be asking the same things because we're going to be doing that over and over for expected value. Anytime you're doing any of those chapters that ask for the expected value, it's going to be the same thing. Okay, and I'm hoping that no one in my class is going to be like, I don't know how to do e of x squared. Because if you know how to do e of x, then you know how to do e of x squared. And I just slammed the table so that it's like just went to the next table. Anyways, here we go. Next slide. So we've got e of x down. Two more terms, and this is called the variance. Variance and then standard deviation. This is the formula, the theory. I want you to copy this one down. Variance, VAR for variance of your data x. It doesn't have to be discrete, it can be continuous. It is E, which is the mean or the average of your data x take away mu all squared. Now the question is, what is mu? Mu is another symbol to describe the expected value, which is the mean. Okay? So write that note down. Now, I want you to think about, I'm going to try to describe this theory about variance to you using my psychology background and what I did when I was at university in terms of data, so it makes sense to you. Okay?
So wait, so if u is mean, which is e of x, is that like expanding the bracket there? Is it e of x squared take away e of x all squared? Do you know what I mean? Is it e of x squared in the bracket take away e of x squared outside the bracket?
Yeah. That's actually the next formula on the next page.
Aha.
Yeah. It's the computational rule for it. Yeah. It's actually what you just said is this, wait, not that one. It's the next slide, that one.
Yeah.
E of x squared minus e of x all squared. Yes. Okay? It's good. Yes. Even though it's not exactly, when you expand this, remember it's you expand it, it'll be 2 minus u, but if you go through the proof, it actually cancels out. So you're on the right track. Remember, when you expand a binomial, there's the middle bit, but the middle bit cancels out if you go through the proof for it. So there's a proof. Minus 2 times mu times x. Yeah. But anyways, right here, whoops, don't look at that, don't look at that. Now, what is variance? Okay, so you understand what the mean is, you understand what the average is, it's the long-term expectation, right? Now I'm going to try to describe it like this now. Let's think, I'm doing a psychology study, right? And I'm going to say, I'm going to study every one of my students in year 12 right now. I'm going to say the number of hours you study, okay? I'm going to make a prediction of what your ATA is going to be. Okay, per day, right? And let's say I'm going to get you to interpret this now, okay? No mathematics, I just want you to interpret with your own gut feeling and tell me this. Okay, I'm going to draw a couple of dots. Each dot represents my students in year 12, and this is my data. Tell me what you can interpret from the data, okay? So I'm going to go with this now. Let's go with this. Whoops. What does this imply? What do you feel when you look at this data here? This is my number of students. This is the ATA to get 99.95. And this is 24 hours. Okay? This is per day. What does this data that I've just drawn imply? Aaron? Kind of, yes.
So there's quite a strong correlation between hours and ATAR, that the more hours you study, the higher ATAR.
Okay, good. So you just said a couple things. Looking at this data, there was a trend, right? We all had a gut feeling that there's a trend that the more hours you study, the higher your ATAR is. True? Based on what I've just drawn. Now, let's try this one. What if I did it like this then? What if I changed the data to this?
Oh, that guy there must be smart.
What does this imply? What do you get? What's the feeling that you're getting? And it doesn't matter the number of hours you study, you could, it's a randomized thing. You could either get high or get low. There's no correlation in any way. No, I'm just making it up. Okay? So, now this is the data. Just keep going with these scenarios. I'm going to get you to think something later. Now, what if I did this? I'm going to change this data to this now.
Oh yeah.
No,
that's accurate. I like that.
Now, my question is, what does this mean? What does this imply? Yes, man?
I was going to use further speak, but I don't do further. The less hours you study, the higher ATAR you get.
Good. So this is now implying that the more hours I study, the less I will get. Well, the less hours I study, the higher I'll get, right? Now, I haven't taught you anything about variance. I haven't said anything about standard deviation, but you guys just did your own internalization of my data and you interpret it, right? What did you do? Oh, actually, before I get to that point, what if I change the data slightly? Okay, I'm going to change it like this now. How's this different to what you just said to me just now? Not much. What's the difference?
So one forms like almost a rule, like it's a linear line, but this one's got room for, like, what's the word for something that's not formable? Yeah, it starts with E. Exceptions. It's got room for
Exception or
exceptions.
error? What you're looking for is error, deviation. And you see this data that I just drew now compared to the next one, the one that we just did before, I'll do it in green. This is very key as to why variance makes sense. Here we go. So what you just did intuitively is that the green line, it was like a prediction. I can almost predict that the person who studied 5 hours has to have this amount. It's predictable. But the more variance or the more error or the sort of how spread it was less predictable. True? And how do you know if something's predictable or not? You took the data that you currently see and you had this imaginary line in your head that it was going down. You had this imaginary line and you said, well, it's a bit off. That's why it's unpredictable. But if it was as linear as the one I just drew, a pattern that emerged, you had a model, you had an expectation. And if it deviated from that expectation, you would say, well, it's unpredictable, right? So when I drew the green line here, you were like, yes, that was very predictable. So what is variance? Variance is exactly what every one of you just did just now. You're looking at how far away it is from your expectation. This is what they did. When you say data, which is what you guys have, minus what I expect. You see, I could expect you in terms of the green line, if this was my expectation. That's my green line. The red is my data. Red is my actual real data. You guys are sitting either above my expectation or below my expectation, okay? But the only way to know that expectation, how far off I am, I might have said, oh, look, Shirley, if you studied 12 hours, you should be getting a 98 ATA, right? But then maybe you didn't get a 98, maybe you got a 65, right? I'm just making it up right now, yeah. Oh, got you. Yeah. Now, you got either 98 or 65, right? Here's the problem. How do you know what the difference of my prediction, how bad is my error? How bad is my prediction? The only way to do that is you take the actual data from the student. So if they got 98, the takeaway is the data they expect them to get. So let's say I expect them to get 50, right? Then it'll be 98 take away 50, and how much am I off? I am 48 off. Okay, now you can say, Mr. Tran, you made a prediction of 48 off. And I'm like, well, that's only one error. I only had this one student, maybe because I don't like them. Okay?
Oh, come on. You out here your mind.
I said them. I didn't say her.
Oh,
Please. Tomato, same thing, okay? Anyways, here we go. So, if we're going with this idea that I've got 48 wrong here, but then the question is, am I just equally as bad for every other student? So maybe for every other student, I'm 48 off. Now, the only way to know that is you want to see on the long term, what's my error? That's what variance means. I just moved it away. Here we go. This is what variance is describing. We did x minus mu, so your data minus my expectation gives you a distance. I'm doing e of it because I want to know overall what's my error. Now why, can someone explain to me why logically I need a square? What was wrong with it? It was fine to find the distance, and it was fine to just add them all, divide it by the number of numbers, and I'll get the average. What was the issue? Steph? Very good. You see, because let's say I predicted you get 70, and then someone got 75, so I'm 5 up. But then what if someone else in my class got now 65? I'm equally as bad. It is 5 off in the negative direction, or positive 5 off in the positive direction. If I ask you to find the average of just those two students, you do 5 plus the negative 5, and then divided by 2, technically I've now got 0 error. What does that mean? It means that I'm so accurate, but I'm not. In fact, I was 5 off. So that's not accurate. So what we do is we say, all right, how do we get rid of a negative? We're going to square it. But if we square it, let's have a look at this. If I was 5 off here, and then I was negative 5 off here, and if I square that, now they're both equal in the sense that, yes, I've got the 25. It makes sense. If I sum all that together, divided by 2, that will give me the average of my error. What's the issue now?
There's two beings who subtract from the original thing.
Something easier. The 25, how much was I really off? 5. 25, how do I go back to 5? So, variance tells you an overall spread as my error, but the problem with variance is it doesn't describe my error as accurately. It does solve the issue of having that counteract of the negatives. So that's why standard deviation, you just figured out standard deviation on your own. I didn't tell you any of this. You guys figured it all yourselves. You knew what variance was intuitively. You knew that the negatives would cancel out, and that's what standard deviation is. Standard deviation, square rooting the variance, because if I had 25, square rooting that now gives me my positive 5, so that's the 5 error. But the variance just describes the spread. It tells you, like, overall, how bad is my data. So if you see a lot of spread, you're like, oh, that's very bad, it's unpredictable. The more close the data is, that means the less error. Less error means less distance. Less distance means it's predictable. Okay? And so therefore, this just tells you the spread. Standard deviation, I'll just rub off all the pictures here so you can see. Standard deviation was square root of your variance. Because if I square root my average, then on average, this is more of my correct error. That's what standard deviation is, and that's the difference between the two. How do we feel about that? So expected value was your average in the long run. Your variance is what the actual data is overall, on average, how bad is my error from my prediction? Okay, my expected. What my expectation was, how far off was it? But the problem was that I had to square it to counteract the negatives. But when I square it, it's now exaggerating how bad I am. So I might have been 5 off, but by squaring that now, you're saying I'm 25 off. I'm like, no, I know I'm bad, but I'm not that bad, right? So because it's squared off, then the only way to really know how much my error was if you square root it. Because you squared it, then square root it. But this time when you square root it, make sure to take positive. That's why square rooting gives me my standard error, or standard deviation. Yes?
So like further that it can only be normal distribution, the data set, because it's got the 68, 95.
That's a different issue. But yes, it's along that idea. Yes. So it doesn't have to be normal. Normal will be split up into those data. We're just talking about, as a general sense, what is standard deviation? What's the purpose of it?
But it can be anything then?
Yes.
Oh,
So you can have an increase. So you're going to learn in sampling, you're going to increase your standard deviation or you decrease it. But obviously, if you increase it, then you affect something. Either number of population or number of people you have in the data, that kind of thing. Yes, Trent?
When you're stating your standard deviation, you just give a number like 5, or you like.
Yep.
You should just say plus or minus 5, like not really your actual standard deviation.
No, that's now moving on to something else. We're going to get to that's now talking about confidence interval, which you get later on. But right now, as just a theory, for you to understand variance, expected value, standard deviation. Now, just before you all pack up, I wanted you to copy two things. Wait, before you go, variance. We use the symbol sigma squared to represent variance. Sigma, because you square root it, that's your standard deviation. And what Aaron said before you all leave, I want you to write this down for tomorrow's lesson. Okay? This here is an easier rule to use than the theory that I just gave you. But everything comes from a theory. It's kind of like your first principles. Knowing your first principle is great, but power rule, chain rule is better. This is your theory to find the variance. This is how you would calculate it. So copy that one down, because I don't think that's in your formula sheet. I think what's in your formula sheet is your theory. And you don't want to go with that. That takes too long to do. Okay? Copy that down. Other than that, I'll see you tomorrow. 3 things to cover. Expected, variance, and standard deviation. Cheers up. Cheers up. Yes. Yep. But I don't know where it is now.